everybody, and welcome back to another episode of Adventures in Machine Learning. This week on our panel, we have Ben Wilson.
Hello.
Daniel Svoboda.
Hello.
We also have Francois Bertrand.
Hey.
I'm Charles Max Wood from devchat.tv. And this week, we're going to be talking to Ekrem Aksoy. Did I get your name anywhere close to correct?
This is 100% correct.
Awesome. Do you want to introduce yourself real quick? Let everybody know who you are and why you're famous.
Sure. Yeah. I've recently completed my PhD on attention and visual perceiving, and I'm working on GeoTap's analytics and optimization team as a software engineer. And yeah, basically that's it.
Good deal.
I remember working my tail off to become a senior developer. I read every book I could get my hands on. I went to any conference I could and watched the videos about the things that I thought I needed to learn. And eventually, I got that senior developer job. And then I realized that the rest of my career looked just like where I was now. I mean, where was the rush I got from learning? What was I supposed to do to keep growing? And then I found it. I got the chance to mentor some developers. I started a podcast and helped many more developers. I did screencasts and helped even more developers. I kind of became a dev hero. And now I want to help you become one too. And if you're looking forward to something more than doing the same thing at a different job 3 years from now, then join the Dev Heroes Accelerator. I'll walk you through the process of building and growing a following and finding people that you can uniquely help as you build the next stage of your career. You can learn more at devheroesaccelerator.com.
So you wrote this article about human attention and its implications for machine learning. And when I read it initially, as I've talked to people about machine learning, a lot of folks kind of explain that the metaphor for machine learning versus like the human brain, or artificial intelligence versus the human brain, only goes so far. And then, I read this article and you're talking about all of these other aspects of how the brain works and how that applies to machine learning. So I guess we should start by what prompted you to write this article, and then I'd love to dive in and say, okay, so how far does this metaphor go?
So let's start with my thesis topic. So I also working during my thesis in I4 Lab, where we were developing an autonomous transportation vehicle. And part of me was trying to create a so-called situation awareness component based on computer vision only. And it turns out there is a hypothesis like, how the things that grabbing our attention affecting our driving decisions. And this question is actually really got me. And, I started deep diving into understand first, what is visual attention mean? I mean, like in a human brain, what are the things that things are grabbing our attention? So I deep dive in that part, and this is basically related on the neuroscience, which I'm not having a PhD or a background in that field. Basically, all our things that we're doing in AI ML, as you said, has something related to neuroscience, or at least metaphorically. But this thing is really coming from neuroscience. So it is, albeit there is no clear definition of attention. I mean, even the neuroscientists can't say this is the attention. So there are many running theories around that. Having said that, basically, I found that there are two forms of it. So first one is that it is very obvious that we are moving our eyeballs, right? And this is because we have a retina, and retina has is corresponding a limited computation resource. So we don't want to process everything that we see. So this is how brain works. So it is evolved into a way that it gets some of these information, but not processing them all. And where we are, or how we select these inputs, are the things that, I start thinking about and, deep diving into that. So this is where it basically starts.
It's kind of like a dimensionality reduction by filtering out irrelevant information.
Actually, and there is a definition in neuroscience in that way. Like, it's like a gain control. Like, you select the subset of the input. So you don't need to process all the information because your processing capability is low on that front. So,
which is a massive departure from traditional dimensionality reduction like PCA, where you're saying, hey, I'm
yes.
taking all the data and I'm trying to sort of average out what the vector is. And
maybe you can think of it like, it's an encoding process. So because the encoding is also what we try to do is we are trying to find the representation of the data, which has, enormous dimensions. And in the ML, what we get in encoding, we reduce it down to some narrow subset of the entire real numbers, for instance. But I also found out that this is the interesting part. There's also something called covert attention. And this part is not related to our eyeballs, but it is more like something that that's grabbing your attention, like you see a red ball, for instance, rolling, or some dog is barking, like you say, and you just turn your head and see the thing there, trying to find the things there. And basically this covert format is more similar to what the AI ML is trying to do in that front. The other one, the overt form is like, we can track from your eyeballs, as Jarvis did it. And this is called saccades. We are constantly moving our eyeballs in the small movements, and it's like, scanning the visual perceived area. And then we go and process the information, what we get from this visual scene.
But when we're talking about autonomous vehicles and their image processing that they're doing, I mean, you can do a brute force approach if you throw enough hardware at it. You're like, hey, create masks for everything, identify everything, and then quantify what the risk assessment is for everything that I see on screen. Computer can do that. We can't do that very well. But your approach, it seems like you're mimicking how our brain, at least in your thesis paper, from what I read, you're trying to get that attention focusing for what we would consider as like peripheral alerting that's happening. Like, just pay attention to the most important elements that I'm seeing on screen in this image in order to detect a risk that I say, I need to press the brake now so I don't do something crazy with my self-driving car. Yes, so when we're talking about doing that in a self-driving car, we're processing a video feed. So how do you construct your actual model architecture to support the concept of that time frame?
It may not be just a video feed, right? It may. Or are we talking specifically about visual stuff, or are you talking about like LiDAR and stuff that we put on top of cars and things like that?
Well, this approach can apply to that thing, but the basic, when we try to apply this thing, what we call in the lab the situation awareness component, I've constrained myself just to computer vision. We can apply the same thing to LiDAR, but the basic problem with the current approach in self-driving car or autonomous vehicle in general, it's like, combination of lots of sensors like LiDARs, radars, the vision, many vision components, such. So the fusion of these information is also creating another problem. And beyond that, human drivers don't need LiDARs or radars, right? Yeah, they are assisting us, but basically we can drive just with our stereo vision. So why can't an autonomous vehicle do the same? So that's also another part related specific to my thesis. And the basic approach here was, I need to create a constrained environment. So I choose braking, and braking is a spatial driving decision. It's not like, steering or like speeding or slowing down, because we know that people has many motivation to steer along the line or speed up. Maybe it's coming from a cheer or joy, but braking is almost always requires something spatial need to happen in your visual perceived area. So I choose braking and try to relate how the salient objects are relating to our braking decision based on this autonomous vehicle environment. That's how my topic is. That's substantiated.
Yeah. Well, and you kind of talked a little bit about the other things that grab our attention. And I'm just glad that if you put this in my car, it doesn't have to turn around and say, "Quit touching your sister."
Yeah, that's also the thing. Or, I saw people arguing with the navigator.
Actually, relating to Ben's question, is there a temporal coherence component to it, or as far as streaming, or is it really just a static image could use the same type of attention, or is it really, or even farther than that, as an eye goes from, let's say, facial recognition, you go from the left eye to the right eye to the mouth to the nose, and is there one, is there a time kind of a temporal component to it, and two, is there anything where there's a modification of attention scanning if, let's say, you go from the left eye to the right eye and you can't find the right eye and then go straight to or is there any kind of live adjustment of this attention?
Yes, definitely. And before answering in detail way, I would like to say that there are two ways the attention is constructed. I mean, besides from covered and overt that we see in neuroscience. And it is coming from bottom up, which, as you say, edges, colors, shapes are grabbing our attention. And this is called bottom-up attention or bottom-up saliency. And there's a top-down, which is constrained by the task at your end. I mean, I can show you a picture of a group of people and I say, find the people with the red hat. So you can just start looking for red hats within the things. This is the top-down saliency. And I can just get you a video feed and you can just start into it and finding the salient objects, a color thing, a shape or just a movement, acceleration, etc. So coming down to your question, yes, it's a temporal thing because first, people tend to find the salient object in static image as well too, but what we have in our visual scene, it is changing. So the dynamics are defined that way. So we need to think about the temporal because in general, finding a feature and trying to track it down to the next frame and such is also the thing in this way, temporal processing of this data. This is and other answer is that yes, it is changing. The dynamics are changing. I mean, if you see a traffic light go to red, it immediately grabs your attention because you have constrained by the context of driving at that moment. That's how you mitigate from potholes. How you mitigate from the pedestrian or cycling guy, so far. So
our internal encoders in our brains have been trained to recognize, red light means stop, pothole means stop.
Yes. And unlike, I see some papers and, some debates on human evolution is providing us these type of encoders, for 1,000 years, but we are not driving 1,000 years, right? Mm-hmm. We can only drive let's say 100 years or more. So these rules are we adopt them. Maybe in near future we have flying cars and we adopt some new environment and their features. So it is always changing its aspects. So it's something learnable. So if something's learnable, we can mimic the same behavior for computers as well, right?
So you have some sort of manually something that you do need to have some human encoding of rules. Is that how you need to handle the top-down part to some degree, saying there's a red object, it's a red light, and it disappeared, and I used to track this. Do you need to keep tracking all features and kind of make a human encoded assessment of what these things mean, then have the machine mostly handle the low-level stuff?
I believe so. The motivation for tracking the red light, for instance, or the pedestrian crossing the road is something that is creating the constraint and creating the top-down. But we also always, this is the interesting part, it is you can always lose your attention, let's say in that fashion, by the context, by something grabbing your attention from bottom up, or you're tracking a pedestrian crossing the road, but you suddenly see a red ball, and it's immediately grab your attention for a short amount of time, and immediately you get back to your attention. That's how neuroscience findings are. So it means that top-down attention is always have higher gain than bottom-up salience.
That brings up an interesting
I tend to slide in. It's not so much that I just get back to the attention of driving. I mostly drive on autopilot, right? I do a lot of things by instinct anymore because I have been driving for 1,000 years, right? So,
yeah, maybe the 101, yeah.
yeah, my mom's been driving for 1,000 zillion years. But anyway, so it's easy for me to slip back into that, right? Because it's just something that I do a lot, especially now that I have kids. But you look at that versus a newer driver, and yeah, if they get flustered or distracted, it takes them a lot longer to get back into that. And so I think that's an interesting element of the machine learning algorithm, getting back to the thing that it's good at pretty quick. So there may be a thing that pops up. One thing that I'm curious about, though, is you mentioned pedestrians versus potholes versus red lights versus whatever. And I guess my question is, they're all kind of different kinds of things, but do you actually specify between, say, a pedestrian versus a cyclist versus another car that moves in front of you versus just, hey, there's some object there I don't want to hit?
Yeah, that's the basic idea. We don't want to create multiple detectors for everything, like pedestrian detector, lane detector, pothole detector, and so forth. So what we want to do is we want to create let's say it's a universal detector that something is getting your attention. In thesis, I can only push this thing forward to supervised learning. So we gave them some data sets, including telematics of the vehicles, and we can label data like, right now this vehicle is braking, and this is where drivers' attention are. So using this relationship, is basically learns how brake is related to something grabbing the driver's attention. Mm-hmm. So this is supervised session, but maybe in later in future we will have self-supervised or semi-supervised or totally unsupervised approaches that can find the attention and find what to do. But eventually, it's come down to, it either need to learn by experience or learn by some human augmentation, like, supervised way, or some other way that is telling, okay, this is right now, in this moment, the right position should be brake.
So what are your thoughts on simulation training for reinforcement learning for something like this?
This is really important because, as you know, in autonomous vehicle, the hardest part is you can't simulate, you can't have accidents. You can't have anomalies in driving data because you can't, design accidents. So simulation is really important. That's also another aspect of my thesis. We also applied findings into using our simulation data. So the importance of simulation is you can create any scenario that you want, like, pedestrian crossing and a car having an accident. You don't want this situation to be, it's horrible. So
penalize the model, please.
Yeah, penalize by, and the weight is like, infinity. So, so yeah, you don't want this scenario to be real. So, but how you teach a machine the outcome of this tension or this moment in your visual perceived area, what would be the outcome? So this can only be created in simulation, to my thought.
It's interesting, though, because it sounded like you did some work where effectively you provided it with the data that was surrounding the driver, so to speak, right? So you gave it a video feed and then also trained it off of what the driver did, right? So did they tap their brake? Did they stomp on their brake?
Basically, yes, Josh. So it is, there are public data sets around this. It is driver's attention kind of data sets. So where people looking by just, eye fixation camera in front of driver, looking to driver. And also you have telematics of the vehicle. So you can, just create a relationship when you process the data. You will immediately know that where is driver looking and what is he doing right now or she doing right now by braking. And as I said, speeding up or steering or changing lane is something you can have different motivations. So it is also hard to relate with the attention. But braking, as I said, almost always relate to something grabbing an attention, like a salient object in the field.
So the idea with the attention, is it like it looks at maybe the different frames of a video, and if there's like a sudden change in a frame, it puts like more of a attention to do something. Like, if you're driving and you see like a red light as you're going up, you're not doing something automatically, you're gradually braking. But when you're seeing like from green light to a red light, then that's like an automatic change. So the attention puts more on like the difference of frames or the frames itself.
It is not just the difference of frames. It is more like the sliding window fashion. We have a couple of consecutive frames, and for each frame we extracted features like CNN does. And then we relate them out of this feature. Which feature should I pay attention or should I put weight in? And this is, in mechanical terms, we create this relation using recurrent neural networks with attention mechanism. So, and this attention mechanism is not the neuroscience attention. So also there's two different aspects of attention. But attention mechanism that we see in the AI ML field is more like, a gain control, and it is more like you are trying to get a probability of how much weight should I give this specific input sample out of all my input samples. So using like a second separated window, I might have, let's say, 4 or 5 frames, and based on each frame's features, I can weigh in for that specific decision. It's like, getting 5 frames from background, and at this T0 moment, I have the braking label and my set of input features. And I choose which salient features are important for that braking decision. That's how it works, basically.
And when you came up with that idea, did you like study neuroscience and plan to like reverse engineer it? Or did you more look at like conventional machine learning methods and hack like the algorithm in order to do that, or like a combination of both?
Well, coming up the basic framework of how drivers' attention related driving decision is require you to go through some computational neuroscience, especially literature. And then when applying this thing to machine learning area, I can just go with usual CNN LSTM way of doing things, or recurrent neural networks of doing way. But I also try to implement the gain control using the ML's attention mechanism. So that's how it's come. But without, covering the basic in the computer vision and the saliency and the attention from computational neuroscience, it will be hard to lay down the fundamentals of this work, like, finding relation between attention and driving decision, or how it's, should be constructed. What will be the gold standard in that?
Sure. I mean, I'm very fascinated, by like how neuroscience is reinforcing artificial intelligence, because a lot of the amazing discoveries we are seeing now is that we are reverse engineering, what's being discovered in neuroscience into machine learning, deep learning, natural language processing. And I think arguably some of those techniques were already there. It's just that only now with the availability of big data and the ability to process it, are we able to like see those things in action. So that's probably like why we've been seeing such a revolution in AI as of recent.
Well, I believe so. And our journey to artificial general intelligence, I believe lots of revelations will give us clue or feedback. It is not, I don't believe that, we need to understand 100% how human brain works by, neuroscience way to construct an artificial intelligence that really works. But in order to understand some basic concepts coming from how we learn on and how we improve ourselves or adapt changes, those mechanisms are coming from mostly computational neuroscience papers.
Yeah, your clever implementation with stateful tracking, that LSTM CNN, where you're maintaining that short-term memory.
Yes.
And also your clever and highly consumable imagery that you created in a couple of your blog posts. I got a huge kick out of that, seeing the heat maps. I'm like, this is awesome.
Yeah.
Like he's actually showing exactly where in these images this AI, this deep learning network that you built is focusing its attention. And it's saying, here was a successful detection. We applied brakes at this point because we detected a pedestrian running across over these previous 4 frames. They just bolted out into the middle of the road. And then also you showing the failure one, where it's like it didn't even detect it because the saliency region was so large that it couldn't actually detect that there was a human running across there. So it speaks volumes. When I see implementations in deep learning where somebody is going that extra step of saying, this is the explainable AI aspect of this, it excites me because it means that regulators are going to be able to use this to say, this is why something went wrong. The practitioners are going to be able to evaluate it and say, this is how we need to adapt so that this doesn't happen in the future. Hopefully they're doing it in a simulation environment and not on the streets. But it's, in my opinion, reading papers like yours and going through your follow-up literature that you've written about this, it's more of a serious take on something. It's not just a science project. It's like, this is what this will look like in the real world if we put more effort into this and employ these techniques. So it was really exciting to read all this stuff. Super cool.
Thank you, Ben. I appreciate it. And note for that, maybe it's like, if you want really applicable AI, and for some, it's like, let me give a memory of mine. I'm talking with a Tesla engineer back in 2017, and the guy told me that in 5 years we will see full autonomous vehicle on the road. And I said, maybe technically you can create a fully autonomous vehicle, but I don't think so, because there will be needed for regulation. Like insurance companies will not know why this accident happened. You need to explain how your model thinks about the environment it perceives for each single moment. So it's not like creating a black box for let's last 10 minutes thing. You need to know how vehicle decided on the things that it does in an autonomous way. So this explainable AI thing or AI aspect of the autonomous driving is, I believe, the huge mountain that we need to go over. So it's not like creating a vehicle that can steer itself. This can be done maybe 30 years, right?
Yep.
But having or seeing this actual vehicles on the road is something different. Yeah, we have some pioneers in the area, and people tend to rely on that thing. But for out of sudden, it goes something or does something wild, and we need to understand why this happened. And then like CSI fashion, we go backward and try to. But this is something, it's need to be done in this area. But I believe it will be more important than having these features or these records are built in the model as well. So that's why also it's important to know what is the thing that grabbing your attention or affecting your sensors.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
Yeah, and that becomes even more complex when you're talking about, okay, we might have a dozen systems, much like the one that you researched, running in an autonomous vehicle. Plus, as Charles mentioned, LiDAR, radar. We have all of these sensors on this car. Whatever goes into the input control system for the vehicle itself, that's an ensemble.
Yes.
And there's probably weights on that ensemble. And when there's a model that's managing that, probably a deep learning model. When you start thinking about how do we explain why it applied brakes at this time, it's turtles all the way down when you're talking about the complexity of why it was trained in the way that it was. To a regulator, you can potentially get the explanation by doing a simulation saying, okay, we're going to recreate this exact situation in a safe environment. This is exactly why it did what it did. Okay, we know that. But to the people that are building these models and training them, they now have to figure out why this system did what it did and make sure that it never does that again. And sometimes it's not just, okay, let's train it on this situation. When you get to that level, your training data set now becomes infinitely sized in scope of here's all these things we have to train for. There's not enough silicon in the world to make enough chips to do this computation. So how do we make it so that it can generalize a little bit more? And that's what I thought was so interesting about your paper, was that generalized holistic view of solving this problem. And it's cool.
You're right, man. And it's like, also I would like to add something that you need to compress. After training this model, you have to compress it and put it down into an embedded computer that's running on the vehicle. Mm-hmm. So it's need to act on the vehicle in real-time fashion. So even in the attention thing, right now, people are tending to find way that speed up the training process, because either models are huge with a billion parameters, or data sets are huge. So when it comes to process the data and even the attention mechanism, we have to find some speed up and find some, different approaches to speed up the processing of these models, because the complexities are huge. Even the computational complexities are huge. So, I see a movement and motivation to go through that front. And even, we have the state of art right now, all called the transformers, which is basically attention mechanism. And it is getting the state of art in almost all fields in NLP. And also right now we are seeing in the computer vision as well.
BERT, GPT, they're pretty BERT, awesome. GPT. It's just trying to figure out, hey, what is the most significant thing in this text's corpus? And let's pay attention to just that, and everything else. That's that intelligent dimensionality reduction. And at inference time, when you're actually trying to use that model, that becomes critical. And that's something a lot of people don't really think about when they're talking about edge deployment, or even just real-time REST API deployment for ML, is when you're talking about building a deep learning model, you can increase accuracy or recall or precision in whatever you're trying to do by just throwing more layers at it or throwing more data points. So there's more nodes in that. At a point, that model is now, it's processing data through it. So it's computational complexity, as you said, and it's space complexity. You now need more powerful hardware to run that in production. And I think that BERT GPT has proven it out to everybody in the NLP community of, if I'm trying to do sentiment analysis or something, I'm going to use, most people are using this model now. It's definitely proven itself. But on the vision side, I don't think people have actually proven to themselves that this is the approach yet, but I think that's coming.
Yeah, you're right. And it's again coming down to, for instance, you can squeeze BERT or GPT into a single cell phone and having it to run in offline fashion. So right now, for instance, we have access to GPTs through APIs, but it's require internet connection right now. Mm. And this is something that you can expect on what I say safety critical cyber physical devices, like cars, like planes, for instance, or drones or whatever. So it is like it need to decide on board in real time. And that's another challenge of incoming AI/ML research area, I believe. And I also believe, since we know the most efficient computer right now for pattern recognition is human brain, and it is consuming really, really small amount of power, I believe some revelation come from neuroscience as well. Oh yeah, that's a cool idea. Let's try to apply this in AI/ML. So I believe we'll see those type of cross-boundary transfers from neuroscience research into AI/ML research, I believe. Yeah.
I'm wondering a little bit if it goes the other way too, right? Where if you get this model to work in specific ways, if it might say, hey, we recorded all this when a human driver had an accident, and it looks like it was because they got distracted by, it pulled their attention to something else.
Yeah, another aspect of this approach, this research can be applied in that way, like assistance to the human drivers. Like, oh, you need to pay attention to this, like, ahead of time. It can, because we know that computer vision can have higher resolution than human eye at some point, like, night vision, etc. So it can warn you, like, you can pay attention to this, or we can retrofit the thing and say, okay, we have this accident, but based on the camera recordings, the driver is distracted. I mean, right now we have these equipment is available on board on many vehicles, like eye fixation cameras and front-looking cameras. So we can have these type of features can be collected right now. This can be happen, but processing things and coming with new models that utilizing these data is something that I believe we will see in the near future too. So we can have, oh yeah, please pay attention to children playing in the left parking side. So those type of warnings. Right now we don't have these, but we can only have warnings for right in front of us, like in our collision course, like pedestrian coming into the road of the vehicle and such. But it might be a generalized view, like because we also know human drivers are paying attention to the environment as well. We are not
Right.
focused on just the lane in front of us. We are also trying to infer the data, like oh yeah, there are children playing, so I need to be more careful, maybe slow down a bit, because their ball can just get into my lane and such. So this type of relations are always coming from neuroscience. Yeah, we'll see those type of different model appear, I believe, in the near future.
I think it's a pretty hopeful message that on the neural level you can see higher performance without having gigawatts of electricity fed into it, fed into a model. So that's a hopeful message that there's some neat tricks remaining to be discovered.
And in that front, maybe you all are aware of the neuromorphic computing, just trying to replicate the exact brain circuitry on the silicon. And I believe IBM had some sort of chip, albeit the programming model is not really straightforward for our computer programming fashion, but it is more like spending low energy for doing the AML computation, especially for pattern recognition, not for sequential processing of data.
Yeah, on silicon models where you can actually upload different weights to that circuitry. I think that's pretty fascinating. And from what I hear on the rumor mill, some chip device manufacturers are working on those plans. I mean, some people have already done it, embedded, algorithms on silicon. But I expect in the next several years that there's going to be standardized versions of very popular models that somebody like NVIDIA is going to talk to their foundry and say, hey, we need you to make these chips for us. And GPT-3 is actually, for instance, is on the silicon itself.
Yeah,
so your
running on the
times or training times is just blazingly fast because there's no conversion layer in there. You're talking directly to the underlying below kernel chip level for that. So that's going to be exciting, I think, for ML practitioners in the future.
Well, I believe so. I'm really positive on that front. It will be really wide spectrum of revelations and progress will come. As I said, models on chip like ASICs or SoCs or spatial processors. And it's not just the GPUs. We also see some conversion in the HPC, right? And this will give us a huge amount of, I believe, new possibilities. That things that I mentioned, for instance, the unsupervised attention for autonomous driving and such. So these things definitely require huge amount of computation and a huge amount of computational power, but we have a constrained resource, the onboard computer. So I believe, but as I said, I'm positive on this.
So I have a question. A friend of mine lives kind of near me. We're about 4 hours or 5. Well, I guess it's 5 hours or so from Las Vegas. And he actually works in his Tesla while it drives itself to Las Vegas. Is that crazy?
Well, it is for right now. I can't trust an autonomous vehicle to drive me like 5 or 7 hours, because driving is really crazy. It's like walking in a minefield. Yeah, it is. From statistic perspective, you have really low chance to spot on a minefield, but it happens.
Right.
So, I don't want to take this risk right now, unless the autonomous vehicle can give me some confidence about how it behaves. That's why I don't want to. Yeah, I mean, right now I don't know how, for instance, Tesla's autopilot behaves. I don't know. I'm not 100% sure. It just decided to run in front of the fire truck, for instance. This happened, right?
Yeah, I think about the only place that I would trust driving like that and focusing on writing code, for instance, would be the highways around Las Vegas or the Route 2 there.
Oh, yeah.
There's nobody on those highways for many. I've been in that area of the country on a road trip before. And I haven't seen a car in 3 hours. So in that case, sure, drive yourself. I wouldn't do it in, say, Boston.
Oh, yeah.
And be like, hey, you can drive this.
Downtown New York, right?
Yeah.
Yeah, fair enough. I think he mostly does it on the interstate. But yeah, it was just interesting to me. He just said, I just turn on autopilot and go. And I was like, wow. Yeah. And there is the possibility that some animal will come out of the road. But yeah, you're right. There isn't really that high a likelihood that something's going to pull out in front of you that wasn't already on the highway moving as fast as you. So
you're right. It's really dynamic scene coming down.
Yeah.
The safety critical vehicles are always having this dynamic environment problem, right? Even the planes. Yeah, it's in a clear airspace, but it's not 100% confident that you can behave autonomously.
Yeah.
I think the idea of having memory vastly improves everything, because before the idea of memory with BERT and transformers, the computers would look at all the data streaming in and they would react immediately, but they wouldn't react with any context. And memory is what allows us to see everything in context. Like where I live, it's almost a heavily wooded area and there's deers coming out. And if a computer didn't have any memories or look at the context of those woods and say, oh, there's a high probability of, deer coming out, then it wouldn't be mentally preparing itself in that context. But when it sees all these wooded areas, or maybe when it sees on a news that there had been all these deer accidents, then it would know in its mind, based on these surroundings, I should be more highly cautious than before.
You're right, Daniel. And the advantage of having these research on AI ML over neuroscience is that we can have a collective memory, right?
Yeah.
Unlike human brain, we can collect all this information in a standardized way, and so 1,000 other drivers' memory can improve my model's driving performance as well. So those type of advantages for autonomous vehicle over human driver is, I believe, will be much clearer in near future, and will increase the performance of autonomous vehicle maybe more than human drivers.
Yeah.
If it's not, yeah.
I mean, I think maybe, and I'm not a neuroscientist, but the way it would improve even much more is if you're taking it as a metaphorical baby and then raising it as an adult, because babies are to little children, they're very, very elastic. They absorb everything uncritically. That's the prime time to learn languages and everything like that. And then by then, they form their own viewpoints. So when people learn, they have to learn it through that narrow filter in a way. So maybe as neuroscience and machine learning progress, we might see a lot smarter self-driving cars if trained in that context.
Yeah, maybe think of it as a child that is trained to be driver.
Right.
So no other business, no other job. So it doesn't need to be generalized in that broad way, but it is just something just focusing on driving, but getting all the aspects of driving, within the computer vision. Maybe this is, fed and supported by some general computer vision abilities as well. But yeah, I agree with you.
Yeah, it really comes down to which baseline CNN you're using for transfer learning. Like in yours, you use VGC 16, which that's an awesome model. It's pretty broadly generalized object detection and classification. So that's the key for the computer vision is how good is that? And you can train your own, like build your own architecture, and much simpler and far less complex than something like VGG or ResNet, just by hand coding it and saying, this is how many layers I'm going to do. This is my pooling layers, my softmax for classifier, and then I'm going to train it on my data, my specific data. But for self-driving cars, applications like that, which are exposed to the natural world and exposed to non-deterministic behavior that might happen, the more generalized that you get, the better, I think.
Yes.
But training those to make that raising from infant to master level classifier, that driver who has that computer vision, that requires a lot of images, a lot of well-labeled images. And who's got the power to do that? There's a few institutions that can make those. It's usually the big folks in the room that are the Google out there who can say, you know what, we've got 150,000 GPUs sitting around in our data center not doing anything. Let's train it on 150 trillion images that we have at our disposal. Yeah, it's going to take about 6 months to train, but it'll work okay.
Yeah, and that's I believe the biggest problem of AI ML research right now. It's like I am old enough to see my computer is bigger than yours area. And right now, what we see is my model is bigger than yours. It's like parameter, parameter. Yeah, like it's a billion parameters. Oh, I have 2 billion parameters in this model. So it is coming like that, as you said. And this is the biggest problem. For instance, many people use, as you said, VGG or ResNet, not just because they are not able to create their own models to extract features, but these models are pre-trained on ImageNet, which takes weeks on GPU. So not everybody has this feature. So we are just using these pre-trained models just for extract features. And we want to do it that way because ImageNet kind of data sets are really wide enough to generalize all type of computer vision scenery features within them. So maybe the other approach might be like the unsupervised vision, right? You can say, okay, you have this vision, you don't need to do anything without, extracting things and such. Please try to extract some features, use this in your pipeline, focus on some specific context, and give me some decision. And I will say, this is right or wrong. And when I say this is right or wrong, I can do this through my as a human, or I can give you another model that's competing against you, like the guns does. And this is really the Achilles heels, I believe, for AI ML research, and this will be creating a bottleneck even more in the near future, because the more data we have, we need more computation. But as you said, only few institutions have enough resources to do this type of research. Otherwise, it will take. I read somewhere, maybe I'm wrong, I'm just throwing out wrong numbers, but it's like, taking $1.6 million for training and GPT.
Yep. Pretty much.
So, yes. So it is something that we can't do. Also, there are other aspects. I also hearing the green computation stuff, and it is like, in order to train an autonomous vehicle, it will take much more emission. It will create much more emission than, having gasoline vehicles. So
yeah, and
this is
my prediction. My prediction for the future that follows on from what you're saying is, I don't think it's just going to become a bottleneck in the next 10 years. I think it's going to be an arms race. As the major tech companies that are competing with one another for relevancy, it's going to become who has the better image classifier, who has the better natural language processing deep learning library that they built that is freely used by people. And the competition is going to be, I think, beneficial to the end users, the app, like people that are like applying machine learning to their business use cases. But anybody who wants to get into designing new algorithms and coming up with custom solutions for their use case, doing it the brute force way of building it themselves, I think that's going to go away because of that arms race that's going to accelerate to the point where nobody else can compete with them. Unless you have your own data center, which most people are in the cloud now, you don't have your own data center. But if you have AWS-sized data center or a Google-sized data center, like, do you have $4.5 billion to invest in hardware and a $20 million a month electric bill, or your own power plant that you've built to support that? If you're not playing at that level, you're not going to be competing with those groups because they have the resources to build the next generation of these.
Yeah, and it's clearly show us that this path can't be lead us to way to AGI, right? So I'm coming back and say maybe a different hardware architecture or computation architecture need to do this, and this
like
is
quantum,
like quantum. Oh, maybe I have zero knowledge, or maybe one. It's quantum, right? So
somewhere between 0 and 1.
Somewhere in 0 and 1 knowledge about it, and I can't tell unless you open the box.
That's a math joke, everybody.
Yes, yeah. So yeah, but as you said, with current infrastructure or current roadmap, we can't reach to a really cheerful AI environment. But what we're gonna end up in another AI winter, I believe. As you said, it's become an arms race. Maybe models exportation will be prohibited or constrained to use, like, against countries and such. So it's not something that I believe giving us a really productive environment, but maybe a paradigm change, like AI infrastructure, hardware infrastructure, models, and such will give us the ability to achieve.
To basically democratize that to the point where there aren't just 3 companies or 4 companies on the planet dominating this landscape. Yep,
you're right.
I mean, I'm hopeful for that as a future.
Yeah,
and there's a lot of companies out there that are.
I would like to stay positive as well.
Yeah, I mean, there's a lot of startups that are focusing on open source development to promote this, and a lot of companies that they are for profit, but they are devoted to enabling as many people as possible to use relatively cheap hardware to solve problems without relying on these prepackaged solutions that are locking people in.
Agreed.
Yep. Super cool. So what are you working on next?
Well, as I said, my next thing will be working on self-supervised or semi-supervised or in general unsupervised way to creating attention like we do. So maybe coming up with new algorithms so we can apply these things directly. And there is also, it's also not something completely in dark. It is like, I see some research on attention in the unsupervised approaches, like, variational inference area. And it is getting really cool results. Like, I read some paper, they are creating scenery out of nothing, giving just a few sample scenery images. It can create create the 3D view of it. So this requires, it need to create a context of the scene it perceives. So this gives me some other idea, so I can apply the same principle to autonomous vehicles, and autonomous vehicle can simulate what will be what can be in the road ahead. So it can give us some warnings ahead, and or create some scenarios, simulates and predicts what might be the outcomes of my decision. So yeah, I believe I will continue in that area as the next research.
Man, that's fascinating. Like, so simulating, say, the next 60 frames of what that video signal would be, and just saying, hey, don't try to render the entire scene or create a matrix of the entire scene. Just just this thing that we're worried about, what is the probability that it's going to still be there, or this
Yes.
next other thing would follow along to that? That's fascinating. I can't wait to read that paper.
Oh, thank you very much, man. I can't promise the due date. I'm not
That's
coming
wise.
I'm not coming, or bonded by the institutional research. So I am an independent researcher right now. So I can do whatever I want with my own time. So I'm not running or competing against like the conferences or journals, but I will do this research and try to see how it behaves. I'm self-motivated.
Yeah, it's fascinating.
Yeah, thank you very much. I appreciate it.
Cool. All right. Well, let's go ahead and do some picks and start wrapping up.
Hey, folks, I don't know if you've noticed, but I've been working a lot on figuring out how to help people become the most valuable developers on their teams or becoming the top 5% of developers in the field. If you're looking to level up, figure out how to contribute more, get the career you want, get the career that you want that will support the lifestyle you want, then you should check out the Most Valuable Dev Summit. I've invited some of my friends across the community, people that you've heard of, people that have worked on systems that you use on a daily basis, people who have invented new ways of doing things over the years in programming. And I've asked them one question, and that question is, how do you become a top 5% developer? How do you become 1 in 20 of the best developers out there? And so we're going to go ahead and have that conversation with them in interviews on the Most Valuable Dev Summit. And you can find that at summit.mostvaluable.dev.
Ben, do you want to start us off with the picks?
Yeah, everything that we talked about today, please go read the original paper. If you're in anywhere with ML and AI and doing practice work in that in the field, definitely give a read to every single blog post that we're going to link to as part of this. It gives a great overview of how to read that paper if you're not familiar with the concepts that are in there. Ekrem does a great job of explaining it in layperson's terms in a couple of the blogs, and then slightly more technical scientific explanations. And then if you want just the full nerd vision, like read the original paper and it's awesome. But this is kind of where a lot of deep learning is going, in my opinion, and is helping to simplify and explain a lot of the complexities that we see in these applications. So that's my big pick. I had a great time reading all of the stuff over the past couple of days.
Awesome. Daniel, do you have some picks for us?
I mean, I still have like the same pick that I was doing last week in terms of reading the book on credit, where I am getting up to speed on the book was called Debt, and it's about like the modern version of the way we do credit and like how it's not what we think it is supposed to be. And it's like revolutionizing a lot of the ways the financial field, given like what we thought about how people exchange debt in the past was not what we expected. And that it turns out to be like a lot more personal and with human feelings in that context as well. And anyone who's like wanting to do machine learning in the financial field, I would recommend that book because maybe they would come up with some ideas on how to create like ML models that are more human-centric in that fashion.
Cool. I'm going to throw out some picks that aren't ML related. So my accountant called me up and said, hey, you haven't filed your taxes yet. He filed an extension for me, but I've been working through my bookkeeping. And let me tell you how fun that is. But anyway, what's interesting is that I switched from QuickBooks to a system called Xero, Xero. And it is so much easier to use than QuickBooks. I think if I were running like this huge corporation that had a bazillion people working for it, and we had all these different lines of revenue, it'd be a different story. But I'm not, and I don't. So this has been really nice. So I'm going to pick Xero. And then I read the book, The Prosperous Coach. And I read through it and then I worked through it again. And I really, really enjoyed it. And it's changing the way that I'm approaching some of the coaching that I'm doing. So if you're interested in kind of taking your career to the next level, you have some goals, you have some outcomes you're trying to reach, you're trying to learn more, do better, things like that at work, maybe find a different job. I mean, any of that, I am definitely willing to help you. The people that I seem to be helping the most are people that either want to build and sell courses or some other educational content. And I have one client that actually launched that kind of a platform. I have another client that got a 5-figure training deal with a larger company off of his podcast that I coached him to coach. So that's kind of the direction we're heading, is podcasting into some of these opportunities. And then I've also coached a number of freelancers on how to augment their practice and have people kind of come to them instead of them having to go to their prospective folks to start shows and find clients. So if either of those areas are interesting to you, then definitely go check it out. The place to go right now is devinfluencers.com/apply. That gets you on the list. It gets you some emails. It tells you where to go to get things scheduled. It actually takes you to another form so I can get more information so I can coach you properly. But yeah, if you go through that process, then I'll sit down with you for an hour or so and we'll figure out where you're trying to get to and how to get there. And that's kind of what I'm putting out there. So that's devinfluencers.com/apply. Ekrem, what are your picks?
Well, nowadays I'm reading a book called Book of Why by Yudia Pearl. I really like the book. And coming from the neuroscience perspective of attention, I recommend you to look at the Lindsay Gray's paper on attention in psychology, neuroscience, and machine learning. And yeah, those two will be my picks.
All right. If people want to find you online, where do you usually put your content?
I either publish on The Gradient or in my blog posts through ekremaksoy.medium.com.
Awesome. All right. We'll go ahead and wrap up here. Thanks for coming. This was really, really interesting.
I really appreciate you and really thank you for giving me the opportunity here to explain what I'm doing wildly.
Yeah, this was fun.
Yep. All right, folks. We'll wrap up here. Until next time, max out.
Later.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.